I could look at it also as the probability of selecting someone that's within a certain range on this distribution. So here is our mean is 100, and our standard deviation is 10. Okay, one of the ways we could look at this is we could look at this as a distribution of the entire population, but you could also look at it as a distribution of the probabilities that you would find individuals in this population in different areas here. So if you were to take a random sample from this population, could be 1 million people in this population, right? Any number, 10,000 people, 1 million people. You would take a random sample, random person you picked out of here. Well, it's much more likely that you would pick someone out that's in the middle here because it's a bigger area of this distribution. There's more people that are represented there. And when I say, for instance, that when I mentioned when you were talking about empirical rule, we're talking about 2 standard deviations to the left and the right of the mean represent 95% of the population. Well, similarly, if I were to ask you, what's the probability, in this case it's going to be 80 to 120. If I were going to ask you, what's the probability that if you randomly selected a person from this population, that their blood pressure would be between 80 and 120, that probability would be 0.9, right? 0.95, right? 95%. If I ask you, what's the probability that their blood pressure would be less than 80, right? What's that probability going to be? Well, it's going to be what's left here. And what's left here, because these are symmetrical, is going to be 2.5% here and 2.5% here. So the probability that you would randomly select someone that's got a blood pressure less than 80 in this population is going to be 0.25, or 0.025, 2.5%. Similarly, the probability that you would select someone that's greater than 80, greater than 120, is going to be equal to 0.025 as well. Okay, wow, how about this oddball? What's the probability of selecting someone that's greater than 80, right? Greater than 80, right? But less than, oops, this is greater, x is, we do it this way, x is greater than 80, and x is less than, or less than 120. Not one, but less than, let me see here, what could I choose here? Less than, say, 140, cover the whole distribution. Well, that would probably cover this entire distribution, right? Which would be 95% plus 2.5%. So that probability is going to be roughly 97.5% of the is the probability you would select someone in that range. Okay, so there's a lot of ways that we can do this. So I'm going to go back now. Another way for us to look at this. Okay, I'm going to go back now, and I'm going to take a look at putting this, what we've learned here with the empirical rule, putting this to work for us. Okay, and I'll come back to the lecture later in a little bit. So I'm going to open up the document that we have on Blackboard that's called One Lab Session Empirical Rule. Okay, here we go, and I got it open already, I think. Oops. Pull it up here. And again, it's a restating of what the empirical rule is. And notice it's really 68.2%. It's a little bit more accurate, 13.6%, 2.1%, and 0.1%. Okay, so a little bit more rigorous statement of it. But in general, you know, for our purposes, it's good enough to call one standard deviation below or above the mean, 68%, 2 standard deviations to the left and right of mean, 2 standard deviations, and 95%, and 99.7% of the population in 3 standard deviations to the left or to the right of the mean. So I'm going to ask you a few questions now. Okay, so let's bounce through these questions. Assume that the heights of adult Caucasian men have a mean of 68 inches and a standard deviation of 4 inches. Find the probability. Now again, we're looking at the entire population here, right? That's not a sample. This is mu and sigma. So these are numbers that represent the entire population. Assume that the heights of Caucasian men have a mean of 68 inches and a standard deviation of 4 inches, and that they're normally distributed. Find the probability that a randomly chosen individual chosen from this population has a height greater than 68 inches. Well, I don't need to pull up a piece of paper for that, right? The mean is 68 inches. What's the probability that you'd randomly select someone that's more than 68 inches? Well, it's going to be the same as the probability of selecting someone less than 68 inches, right? Or it's going to be 50%, right? Well, how about what's the probability of selecting someone that's between 64 and 72 inches? Well, for that one, I'm going to actually sketch this out. Oops. 68 and 4 was our parameters. So here's our normal distribution. Whoops. And our mean is 68. And our standard deviation is equal to 4. And I think the question asked us, what's the probability of randomly choosing an individual who's between 64 and 72 inches? Okay, 64 and 72 inches. Okay, so how many standard deviations above the mean is 72 inches? Well, that's plus 1 standard deviation above the mean. What about 64? 64 is minus 1 standard deviation below the mean. So we know that this represents approximately 68% of the population, or the probability of choosing someone randomly that's within that range is 68%. Okay, from our empirical rule. Okay, what's the next question? Next question is between 60 and 76 inches. 60 and 76 inches. Okay, how many standard deviations to the right of the mean is 76 inches? 2 standard deviations above and two standard deviations below is 60 inches, right? 68 minus 4, 60 inches. Minus 8, 60 inches. Okay, so what's the probability of choosing someone between these two values of 60 and 76 inches in height? Well, that probability is going to be 95%. 4.95. 95%. What's the probability of picking someone that's less than 60 inches tall? Well, we know that probability of less than 60 inches tall is going to be equal to 0.025. It's only 2.5% chance of picking someone that's that height, because that's the percentage of people in the population. This is could represent that portion of the population, or could represent the probability of an individual being in that area of the population, that part of the population, right? In other words, a population probability density, or above 76 inches tall is also going to be 0.025, 2.5% as well. Okay, so let's move on from there. Okay, so let's take a look at the next question. Okay, assume the heights of adult Caucasian women has a mean of 63 inches and a standard deviation of 3 inches. What percentage of women in this population have a mean height greater than 63 inches, greater than 66 inches, and less than 60 inches? Okay, this might be a little bit more adventurous. Take a look. Let's sketch it. Always helps to sketch this stuff out. Okay, so what does that mean? Our mean is 63 and standard deviation of 3 inches. 63 and standard deviation is equal to 3 inches. This is our mean. And let's see what we're asking there. What's the probability of randomly selecting someone that's greater than 63 inches. Well, that's 50% of the population, right? That's an easy one, right? The mean split this as symmetrical, the mean split this in half. So the probability of selecting someone that's greater than 63 inches is equal to 0.50, 50%. Okay, so what's the next question? What's the probability of selecting someone that's greater than 66 inches? Okay, whoops. Okay, so 66 inches is going to be out here somewhere. So the area we're asked about is what's the probability of selecting someone that's greater than 66 inches? Okay, what's that probability? Where's 66 inches? 66 inches is one standard deviation above the mean. I'm going to introduce another concept here. I'm going to introduce the concept of the idea of a z-score. The z-score is equal to the number of standard deviations from the mean. So 66 is one standard deviation above the mean. It's 3 above the mean, so it's one standard deviation above the mean. Another way of saying that is say that it has a z-score equal to +1. It's one standard deviation above the mean. If I had looked at 60, for instance, that would have a z-score of -1, or one standard deviation below the mean. Okay, and one of the things I can do that's very handy, it's nice that these are even numbers now. They may not always be even numbers, but I can write a formula. Z is equal to whatever value you're interested in minus the mean over the standard deviation, and that'll tell us what the z-score is, the number of standard deviations. So for 66, that z would be equal to 66 minus the mean 63 over the standard deviation 3. That's 3 over 3 is a +1. So that's an easy way, if we get into trouble and we're not sure what we're doing, it's an easy way to remember the number of standard deviations. So the question was, what percentage of this population, or what's the probability of randomly choosing someone that's above 66 inches tall, a woman that's above 66 inches tall? Probability of greater than 66 inches. Okay, what's that probability? Okay, well, what do we know here? We know that one standard deviation below to one standard deviation above is 68%. And that means that 34% is between the mean and one standard deviation below, and the mean and 34% is between the mean and one standard deviation above. And this area from the mean up is 50%. So that would leave in this area 16% of the distribution. So the probability of choosing a woman from this population randomly that's greater than 66 inches tall is 0.16, or 16%. Okay, how do you guys feel about that? I see some of you keeping up with me. Any question about that so far? Are you guys comfortable with this stuff? Are you comfortable with the relationship between looking at this as a histogram, the population distribution, and also looking at it as a probability density, a way of describing what the probability of your finding some part of the population at a certain level? Can I repeat the last part about the population density? Okay. Is that what you're after? Where did I get 68%? Remember that we said our empirical rule? Oh, that's the part you're interested in. Okay. Remember our empirical rule. Actually, I have it here. I have it in this document. Remember, our empirical rule tells us that 68% in the normal distribution, 68% of the population is between one standard deviation below the mean and one standard deviation above the mean. 95% of the population is between two standard deviations above the mean and two standard deviations below the mean. These numbers are a little bit more accurate, but they're really basically the same. And then 99.7% is between three standard deviations below and 3 above. So notice that because this is symmetrical, that in addition to knowing that 68% of the population, or probability, is between one standard deviation below and one standard deviation above, we also know that half of that 68% is in one side and the other half is in the other side. So this area is going to be 34% of the distribution, or 34% of the probabilities, 34% of the population. So when I did this particular problem, whoops, I've lost it here somewhere. Oh, here we go. Whoops, didn't need to do that again. Let me get rid of this. Okay, and get this out of the way. Nope, don't let me do that. I think I closed the wrong one. Yes, I certainly did. Okay, let me get it open again. Sorry for the delay. Okay. Okay, so again, when I drew this distribution, and I described that the mean is 63 and the standard deviation is equal to 3. Well, one standard deviation above the mean is going to be 66, and one standard deviation below the mean is going to be 60. Right? So if I'm interested in what portion, what was the question again there? If I'm interested in second part of this, what percentage of women is population of a height greater than 66 inches? If that's what I'm interested in, then I'm interested in the proportion of the women that are in this area here above 66 inches. Right? So I know that between 60 and 66 inches, one standard deviation below and one standard deviation above. I know between these two is 68% of the population. Okay, so now I could say to myself, well, that's 68% of the population. That leaves 32% of the population unaccounted for. And that's this area here and this area here, the one that we're interested in. Since this is symmetrical, it's got the same shape on both sides. You could fold it over and be exactly the same on both sides, right? We know that these two areas are equal. So if only 32% is left, that's 16% here and 16% here. Okay, so another way for me to look at that would have just been easy, just as easy to say, yeah, 68%, this part is 32 and this part is 32 because it's on either side of the mean, they're mirror images. And what I could do is I could say, you know, this upper part from here to the right is 50%, and to the left of the mean is 50%. Well, if I've used up 32% of my 50%, that leaves 16% here. So I get the same answer, even though I did it a little bit differently, two ways. Are we okay with that? Okay, then let me get to the next part here. And less than 60 inches. Similarly, less than 60 inches. I kind of just answered that question, didn't I? Less than 60 inches is going to be the same situation. It's going to be 16% also. Okay, let's try another version of this. Let's try another problem here. Okay, let me reopen this. And here we go. Okay. Okay, the gestation times for humans has a mean of 266 days and a standard deviation of 25 days. What percentage of pregnancies would you expect to be? Now, we're making an assumption here. We're making the assumption that gestation period for humans, in other words, the time it takes to carry a baby to term, is normally distributed. In other words, it's got a nice bell-shaped curve, it's symmetrical. Between me and you, we know that's not true, right? Because you have a lot of premature births. Yeah, most births are clustered, normally distributed, around something like 250, 260 days. But then you can have a lot of premature births that are much shorter periods than that. It really, in real life, it's really skewed to the left because of those low values, the premature births that drag the average down. However, I'm going to ignore that for purposes of this example because I'm demonstrating the empirical rule. So I need to apply it to a normal distribution. We're going to make believe that this is a normal distribution. Okay, so the mean is 266 and the standard deviation is 25. Let me open up a sheet. Okay. So the mean number of days, 266, and the standard deviation is 25 days. Okay, so let's check out our question. Okay, so our first question is, what's the probability, what percentage of pregnancies, or probability that you would randomly select a pregnancy, and it would be greater than 291 days? Okay, so we're interested in this area here. So let's call that 291. We're interested in the area, the percentage of pregnancies that go more than 291 days. This is not, again, these are not real numbers. We're just doing this as an example. So 291 days. So how many standard deviations above the mean is 291 days? Well, you probably can see this by eye, but in case you can't, remember that little cheat with the z-score. Z is equal to the value you're interested in minus the mean over the standard deviation. So Z is equal to 291 minus 266 over 25. So let's see, that's going to be 25. 25 over 25. It's equal to 1 standard deviation above the mean. So we know this is 32%, and we know this must be 16%. Probability pregnancy going that long is 16%. Okay, just a little bit of a twist there. Numbers a little bit different. Okay, how about less than 241 days? So 241 days, well, I'm not going to repeat that again because kind of obvious. 241 is 25 less than this. So this is 32%. So this, and you remember this is the 1 standard deviation below, 1 standard deviation above, 68%. So this is going to be roughly 16% of the births are going to fall less than 241 days. Okay, how about it's the last one? Okay, less than 241 days or greater than 291. Less than, what did I just say there? Less than 241 days or greater than 291 days. Okay. So less than or greater than, less than this or greater than this. That's a union, right? Remember we were dealing with that. It's either outcome satisfies what we're interested in. It could be less than that or greater than this. Either one of those are criteria that we find acceptable. So that probability of being less than 241 or greater than 291 is going to be 16% chance we're going to be less than 241 and 16% chance we're going to be greater than 291. So the probability of that outcome is going to be equal to 0.32, 16 and 16. Right? It's going to be 32%. Okay, so all I'm doing here is I'm kind of, okay, I'm sorry, let me take a quick look here. I got a question here. Standard deviation is 30, did I say 34 or 25? I think I said standard deviation was 25. Yeah, standard deviation is 25. And 32%, 32%, yeah, is correct. Okay? Not 32, 32%. Well, you can look at it as either a percentage of the population or the number of births. 32% of the births would be less than 241 days or more than 291. Or you can look at it as a probability. The probability that you would randomly select one woman and predict what, whether a birth would be less than 241 or more than 291 would be 32% as well. Of course, it would be 100 minus 32, or 68% likelihood, right, that it's between those two numbers, right, between these two numbers. Oh, I'm sorry. Oh, I get it. Oh my God. Yeah, I had a senior moment. You're absolutely right. I had a senior moment, 34%, right? And 16% is right, but you're right, 34%. Yep. Thank you for pointing that out to me. You are absolutely correct. Yes. Don't let me get that, don't, I appreciate the fact that you cut in there and let me know right away rather than let me drone on for the next half hour with that wrong number there. Okay, so yeah, 34%. So that's our empirical formula. Okay, so now I am going to play another video. Okay, so, and we're going to come back. We're going to take the next step. Well, actually, let me just see what the next problem is. Okay, okay, I'm going to go to problem 5 here. Okay, I'm going to quickly sketch this out. The body temperature of adults have a mean of 98.6 degrees and a standard deviation of 0.6 degrees. Find the probability randomly selected individual has a mean temperature greater than 99. Okay, 98 and 0.6. So let's give that a try. Okay, 98.6 is the average, mu. Standard deviation is 0.6 degrees Fahrenheit, right? And we're interested in what percentage of the population, or what's the probability that a randomly selected individual is greater than 99 degrees. Okay, so there's 99 degrees. So how many standard deviations away from the mean is 99 degrees? It doesn't look that it can that easy. Let's see, z is equal to x minus mu over sigma. So the value we're interested in is 99 minus 98.6 over 0.6. So z is equal to 0.4 over 0.6, which is equal to 0.67. Actually, 0.666. It could be 0.66667. Right? I'm just going to call it 0.67 for our purposes. 0.67. So this is 0.67 standard deviations plus 0.67 standard deviations above the mean. And we're interested in the area greater than that value. So this area in here, well, that's a problem because our empirical rule only works with whole numbers. 1 standard deviation above the mean, 2 standard deviations below the mean, and so on and so forth. So we're kind of stuck. Our empirical rule is failing us here now, isn't it? Right? So I'm going to let this go for now. I'm going to play the next video and let the suspense build on how we're going to deal with this. I suspect that many of you have already taken statistics in the past and you know where we're going with this. But for those of you that don't remember it, I'll let the suspense build. How are we going to deal with this now that the empirical rule is not serving us?